Okay, so let's get started. So let me just first of all give you a little bit of a trajectory of where we're headed. So I'm gonna talk about parallel execution today of Lingua Franca programs, and then on Monday I'm going to go into a fairly detailed discussion of what are the various mechanisms that people have used over time to effectively get parallel execution. Because Lingua Franca uses one particular approach, or it's actually a family of approaches, but it's not the only approach. And I think it's important to understand something about the various ways that parallelism can be handled. And then we're going to start to look at distributed systems. And with distributed systems, things become a lot trickier, because when you talk about parallel execution within a multi-core system, a lot of the hard problems are dealt with for you already by the people who designed the system using a memory model. Okay, the memory model of a multi-core machine is, in a way, a very powerful crutch. Okay, it's something you can kind of depend on when you're writing software for multi-core machines, and you lose that model in a distributed system. And there's some very fundamental trade-offs that arise as soon as the system becomes distributed. Okay, so we make a distinction between parallel execution on a multi-core machine where there's a nice clean memory model versus distributed systems where you don't have that memory model anymore. You don't have a common notion of time. Is the other thing. On a multi-core machine, you can get access to a single clock. And so parallel execution is easier. But it's nonetheless non-trivial. All right. So let me start with actually. Let me do this PowerPointless. I guess I have to get out of PowerPoint show mode. All right, here is a rather simple Lingua Franca program that has, it's a good template for an embarrassingly parallel program, as they might be called. Okay, so there's some computation that takes time. There's some source of data. This source of data gets farmed out to some number of workers, and then you collect the results. Okay, this is sometimes called a scatter-gather pattern. There's more elaborate patterns that have a less simple structure, but they have the same sort of property where there's a fan out of work to be done, followed by a collection of results. Okay, so MapReduce is another pattern that has that kind of character. And that's the pattern that's used in the PageRank algorithm, which is sort of the core algorithm behind search engines. Okay, it's how the indexes get constructed for search engines like Google. All right, so this is a fairly common sort of situation, but this particular program is just a kind of a simulation of a scenario where the worker reaction is this one, and it's just simulating work by going to sleep, okay, in this case. So it just takes a chunk of time for this to execute, and then it produces some result, okay? So let's look at, so there's a target parameter which specifies the number of workers, okay? And the way the execution engine in this case works is that this parameter will determine how many threads get created to execute reactions. And then it relies on the operating system to put those threads on separate cores, which the operating system will normally do transparently, all right, in order to take advantage of multiple cores. So if you don't set this, All right, so let's start with that, and I will compile this program. It's fork join. Second, my computer is wobbling annoyingly. Okay, so it compiled correctly. Let's see. I am in what directory? I think this is the right directory. Fork join was just created May 11th at 15:04. That sounds right. Okay, so that's this. Okay, so if I run this fork join program that just got generated, notice it tells me that it's using 16 workers, and the reason is that there's by default the runtime engine here figures out how many cores are available on this machine. This machine has 16 hardware threads. It's actually 8 cores, but it interleaves 2 threads on each core. Okay, so it can execute 16 threads simultaneously on the 8 cores. All right, and so it uses 16 workers by default. And notice that it executed 2 seconds worth of logical time in 2.2 seconds. Okay. If I specify to use only exactly 1 worker, I'm going to get quite a different behavior. Code generate this again. Looks like it compiled with no error. Run it again. Running a lot slower. Okay. So it took it almost 9 seconds to do 2 seconds of logical time. And in fact, if you look closely at the code, you'll see that the take time is trying to take roughly 2 seconds for each execution of this function. Okay. So let's look at how this actually executes. And here, a blackboard would help a lot, but I'm going to try to do this on my computer because I don't want to try to do this in the back of the room. But so suppose we have 4 worker threads. All right. The way that the Lingua Franca execution engine works is that it uses 2 distinct queues, one of which we call the event queue, which is sorted by the tag, which is a timestamp and the microstep. And the other one is the reaction queue, which is sorted by, I'll talk about deadlines now in a bit, but the first thing to consider is the levels. Okay. And these you can view. There's an option in the diagram viewer to show you the levels that are calculated, but what the Lingua Franca code generator does is it does an analysis of the dependencies between reactions across your program. Okay. And it constructs a directed acyclic graph of all the reactions. And then it figures out how deep each reaction is in that graph, how many reactions are ahead of it. And that number is the level. So this reaction has no reactions that it depends on, so its level is 0. Each of these 4 reactions has level 1, okay, and this reaction has level 2. And then the simplest scheduler is one that just says, well, any 2 reactions with the same level can execute in parallel, because we know there's no dependence between them, right? So how does that work? Well, the way the execution actually occurs is the timer here, first of all, creates a timed event. Whoops. It was supposed to create, creates a timed event and puts it on the event queue. And it's the only event on the event queue initially, because this program is rather trivial. So the fact that it's sorted by timestamp doesn't really matter, right? Then what the execution engine does is pull off the first event on the event queue, determine what the tag is, And then it pulls off all events that have that same tag. Okay. And each of those events has one or more destination reactions that are triggered by it. So it puts those reactions onto the reaction queue, which sorts them by level. So the workers then just pull reactions off the reaction queue from the head. Okay. Since they're sorted by level, this is going to ensure that if there's more than one, then more than one worker can pull them off at the same time. But in this case, initially there's only one, right? This reaction right here. So one of the workers gets it, executes this reaction, which then enables 4 destination reactions. So these 4 reactions get put onto the reaction queue. Oops. So there'll be 4 of these guys all with the same level. And now all 4 workers will be able to pull a reaction off the reaction queue and execute them in parallel. And then when they get done, this reaction becomes enabled and it becomes the only reaction on the reaction queue, and then one of the workers gets that reaction to execute. Okay? So that's pretty simple, but I want to point out that it's a pretty stupid schedule. Okay, you could do a lot better than this by taking advantage of more information, right? The fact is that this strategy that I just described will forego some parallelism in certain circumstances. So for example, if I have, show. If I had some other pair of reactions that were triggered by this same output, and maybe a chain of them, okay, only one of those would be able to execute in parallel with these guys, because only one of those would have the same level. And so one of the things that is going on in my research group, as well as in Dresden and in Kiel, where there's most of the work is happening around this language right now, is various research projects to come up with ways of really taking advantage of the static information that we've got about the program to really optimize these parallel schedules. Okay. There's some very nice opportunities there. Let me show you another example of a pattern. This one, the graphics doesn't render particularly well. It doesn't show very well what's going on. It's a little bit of an open problem to figure out how to fix that. But what's the picture here? So it's a little bit higher. We're sending a message to the first of a bank of reactors. Okay. Then the first one in the bank is sending a message to the second one in the bank. And the second one in the bank is sending them to the third. And the third is sending the one back to the fourth. And then the fourth is sending one out to the receiver. Okay, so it's really a chain of reactors. Okay. There's a total of 4 of these guys in a chain, right? And so this is a similar situation, but here, okay, I've got it set to specify that there's 4 workers working on this. So let's compile this program. And it compiled correctly. And I see that it's really not executing very fast, okay? It executed 1 second of logical time in more than almost 4.5 seconds, all right? And that shouldn't be that surprising, right? Because if I enable the levels here, oh, why is it not showing me the levels? Right, because I need the details. This is a level 0 reaction. These guys, because they're just in a chain, have levels 1, 2, 3, 4, and then level 5. There's no parallelism. So suppose that I wanted to execute these in parallel. What should I do? Yes. So basically what I would like is for the first of these guys to be processing a later sample, while the second one is processing an earlier sample, while the third one is processing a still earlier one. Right. Yeah, I want to pipeline this, right? And the way you do that in Lingua Franca is by introducing a logical delay. So in particular, you can use this after keyword here, right? This introduces a logical delay of 100 milliseconds on each of these connections. And notice now all the levels became 0. Right? So think about it. You know, the first time this guy fires, there's nothing else to do, so there's no parallelism. So this is just going to execute. Okay. The second time it executes is after 100 milliseconds. At that exact logical time, the first of these has an input. Consequently, these two can execute in parallel. And this guy is going to produce a result that will be delayed another 100 milliseconds. So when we're at 200 milliseconds, this will be enabled, the first one will be enabled, the second one will also be enabled. All three of them can execute in parallel. Right? Fourth time, 4 of them will be able to execute in parallel, and so forth. So I can validate that by compiling this and then running it. So notice it executed 1.5 seconds of logical time. Was it 1.5 before? Whoa. That's weird. Oh, huh. No, it's not weird. It's constraining the total number of outputs. It's not using a logical time to stop. Yeah, so it's processing the same number of samples, but taking more logical time because of the logical delays. All right, but it did 1.5 seconds of logical time in 1.6 seconds, whereas before it did 1 second of logical time in 4 seconds. Okay, so considerably faster. But there's a subtlety here, right? If there's no exact match of the timing here, okay, then I still have everything having level 0, but there's not going to be much parallelism. Okay, because the way that lingua franca works is it progresses, remember the two queues that I saw. It pulls off the event queue and then processes everything at a logical time. And then there's a barrier synchronization. And then it pulls off the event queue to advance to the next logical time. Okay. And so what's going to happen in this case is the first of these, well, it'll execute by itself because there's nothing else to do. The second of these, however, is not going to be enabled at the same logical time as the first of these. The first of these will be enabled at logical time 80 milliseconds, whereas the second of this will be at 100 milliseconds. They're not aligned. So they won't execute in parallel. So if I compile this program now and run it, it's going to run much slower. .4 seconds of logical time in 5 seconds of execution time. All right. So one of the interesting things about this is that, you could actually build an execution engine that was, again, more sophisticated than this and was able to advance logical time independently in parts of the system when there's no dependencies between them. Okay. That's part of the ongoing work that's, in this research effort is to take advantage of that possibility. And in fact, I'll show you that the distributed execution actually does that. All right? So we'll see that next week. Okay. So let's look at a little bit more elaborate example. So by the way, one of the motivations for this work is we have a lot of interaction with companies that do embedded software in automotive applications, and a little bit less than some interaction with companies that are in avionics. I mentioned the Airbus tour that I went on before, and most of those companies these days, when they use multi-core machines, they disable all the cores. Because they don't actually know how to take advantage of the multiple cores safely. So a big part of our motivation here was to provide something that will give you exactly the same behavior, no matter how many cores are running the program, and being able to take advantage of the cores doing things in parallel without changing the behavior of the program. It's one of the motivations. So here's kind of a situation that is pretty typical of what comes up, for example, in an automotive case. You've got some number of sensors, you're doing some computation on the sensor data, but you're also doing some fusion of sensor information. So for example, you have LiDAR data and camera data coming in, and you're having to fuse this data in order to come up with decisions for driving the steering or driving the braking. Okay. So pretty common pattern. Here's the kind of questions that we're interested in, right? So if we have sporadic events, so sporadic here is a technical term. A sporadic event sequence is one where you can assume a minimum time between events, but they're not periodic necessarily. Okay. But it's important to be able to assume a minimum amount of time between events. So you have sporadic events that are assigned a timestamp based on the local physical time clock. You might mix that with periodic events. Okay, so maybe this sensor is driven by a clock, and this one is driven by just sensing some condition in the physical world. In lingua franca, the computations have logically zero delay, so the outputs are have the same timestamp as the input, which helps with data fusion because it means that if you get two inputs from your two different sensor sources, you know something about their alignment. Right? They're simultaneous, logically simultaneous, they will have the same timestamp. They're both periodic, driven by the same periodic clock. They will always be aligned, and your fusion algorithm will always see them together. If they're occurring asynchronously with respect to one another, they will nevertheless have always a repeatable ordering. Okay. So that's an important property. Every reactor handles events in timestamp order. And actuators can have deadlines. Okay. And I talked on Monday about some of the subtleties around these deadlines. Okay. But so a piece of fusion code can have this kind of structure. It's a reaction. In this case, it says it's triggered by these two inputs, which means that if either input is present, this code will execute. Whenever you have that situation in Lingua Franca, you should test for presence of the inputs. Don't just assume that they're present, okay, because they might not be. So in this case, we test for the presence of the input, test again for the presence of the input, and merge the results in some way. Okay. The way that the execution algorithm works is that you sort the reactions. Well, this is actually only for sequential execution. So the more general case is you treat this as a directed acyclic graph, and then assigning levels in the graph is one way to be able to enable parallel execution. But the key idea is that you have a global notion of what is the current tag. That's the timestamp plus the microstep. You have an event queue that stores all the future events. You choose the earliest tag on the event queue. You wait for the real-time clock to match the timestamp of that tag. Okay. This is the issue of real-time chasing logical time that I talked about. And then you can execute reactions either sequentially if you just have one thread of execution, or you can execute them in parallel, taking advantage of the potential parallelism exposed by the directed acyclic graph. Okay. I think I have said all this before. Yeah. So the levels look like this. I do want to point out here, might not have seen this pattern before in Lingua Franca, but here I have two reactions that are both writing to an output. Okay. What do you think the downstream is going to see? Let's see two events. So one of the key principles of Lingua Franca is that every one of these connections represents potentially one event at one tag. Only one event at one tag. So the semantics of this is that this reaction will potentially overwrite the output, and the downstream reaction will only see the final result that was written to the output. This is particularly useful. Actually, let me show you the code for this, because it illustrates a pattern that you might not have thought about using, but is extremely useful. So this is this example right here. So here's a reactor that's defined with an input and an output and some reaction. In this case, the body of the reaction is empty because this is just an illustration of a pattern. But notice what's going on here. This fusion reactor extends this computation reactor, which means that it inherits any properties that the base class has. Its inputs, outputs, and reactions, and state variables and parameters and everything else. So this use of inheritance in lingua franca is potentially extremely useful. But because it inherited this reaction right here is the inherited reaction. This one potentially overrides the behavior of the inherited reaction. Okay? So this is the way you can create a subclass of a reactor that somehow elaborates the behavior of the base class. In this case, right. So right. If in one is present, both reactions will fire. If only in two is present, only this reaction will fire.
Right. So I have to, in the body, explicit as to when.
Yes, and you can do that as follows. So, for example, here I can say if in is not present, oops, then set the output to something. Okay, and so this explicitly will write to the output only if this reaction did not write to the output. You can also directly test the output. Okay, if this reaction had set the output, then you leave it alone. Otherwise, you override it. I mean, you write to it.
Is that only work reactions that
So with inheritance, you can't switch the order. The base class always has earlier ordering. Okay. And that's a deliberate choice because it's trying to support this pattern of overriding, but not. It would be a little bit weird if this guy had to test for what the subclass had done.
Can I extend it twice?
No, because then you get a collision of names, but you can extend multiple base classes. So for example, as long as you don't get name collisions. So suppose that this one has an output named out1, then I could extend sensor as well. Okay, and I acquire that behavior. But I've messed things up by changing the name of that. So that subclassing behavior is actually quite powerful and pretty useful for building kind of more modular lingua franca programs. Interestingly, it's not yet supported by all the target languages. The C++ and the Rust implementations don't support subclassing yet. It's in progress. Okay. We talked about the levels already. Reactions with the same level can always execute in parallel. Oh, yeah, it's important to understand that reactions within a reactor never execute in parallel, which you can kind of see now good reason for that, right? In addition to the fact that they share state variables, which would create race conditions if they write to the state variables, but they also have the possibility of reading and writing the same inputs and outputs. And so that having that mutual exclusion keeps things very clean within a reactor. So that means that when you want parallel execution, you need to separate the work across reactors, right? Which is a very deliberate thing to do. It means they can't share state anymore. They have to pass messages to each other. Okay, and that's how you avoid the non-determinism of race conditions with shared state. All right. Here's an interesting twist on the deadline. Okay, so let's talk a minute about the deadline. So if our actuators have deadlines of 10 milliseconds here, and suppose we have physical actions driving these sensors. So what's going to happen is some external event, like a pushing of a button, or an interrupt service routine gets triggered, a network packet comes in, something. An event occurs, gets timestamped. Okay, and then a chain of things happens, and you drive an actuator. The deadline of 10 milliseconds says, I need this to be invoked no later than the timestamp of the input plus 10 milliseconds. Okay, the timestamp was assigned here. So think of it as, button got pushed, interrupt service routine kicked in. The button push got timestamped. So the timestamp is now the time at which the button got pushed. And the deadline says, I want this actuator to be invoked no more than 10 milliseconds after the button is pushed. Right? That's what it says. But it could be invoked 500 microseconds after the button is pushed, or 1 millisecond, or 5 milliseconds, or 8 milliseconds. Okay, so there's actually a lot of wiggle room there, and you might not want that much wiggle room. You might want more repeatable behavior. So here's one way that you can get the more repeatable behavior is to explicitly manipulate the timestamps. Okay, so here I've introduced a logical delay of 9 milliseconds and then a deadline of 1 millisecond. And what this means now is that the actuator will be invoked between 9 and 10 milliseconds after the button push. Between 9 unless the deadline gets violated. Right, so I've greatly reduced the wiggle. So now I'm going to get more repeatable behavior system. This principle is known as logical execution time, and it's something that is actually used in practice quite a bit whenever you want to get repeatable behavior in some kind of control system. This is very useful. Notice also that you can make this deadline very tight because the mere presence of this delay on this input means that this guy acquires level 0. So in addition to prioritizing the execution of reactions by level, we also use deadlines. So a reactor with a deadline and level 0, a reaction with a deadline and level 0 will have higher priority than any other reaction that doesn't have a deadline. So as a consequence, this, when logical time advances to this 9 millisecond point, this reaction will have top priority. These two will have top priority. Consequently, they will execute right away. So we're going to execute very close to 9 milliseconds. Really get the jitter of the timing down on the system. Right? Okay, so logical execution time, or LET, is this principle. You can think of it as this is saying that the logical execution time of this computation is 9 milliseconds. So we get sensor input, we compute for 9 milliseconds, then we drive the action. Okay. And as long as this computation actually remains below 9 milliseconds, you're going to get that timing very precisely. Of course, if this computation exceeds 9 milliseconds, what's going to happen? I'm going to violate the deadline. Okay? And if you remember from last time, the way that deadlines are written is specify a separate chunk of code to execute when the deadline is violated. So if this computation exceeds 10 milliseconds, I'm sure that the deadline will be violated. Your deadline violation handler will be invoked instead of the regular reaction to decide what is safe and what is not. That to handle that situation. Right, so I want to emphasize, to connect with the earlier discussion about determinism. Okay. Is this a deterministic program? Is it a deterministic model? There's kind of a number of issues that get a little bit subtle, right? One, of course, is that the input timestamps are not deterministic. Okay. But if you're given the timestamps of the inputs, right, the program is still not necessarily deterministic. It's only going to be deterministic if the deadlines are not violated. Right? So you have a deterministic model that has now made some assumptions explicit. The deterministic model that can be realized faithfully only under some assumptions. That's true of every deterministic model. No matter what deterministic model you're working with, it can only be realized under some assumptions. And often those assumptions don't get stated explicitly, but here they're stated explicitly. Okay? And not only are they stated explicitly, but you can put into your code what to do if they get violated. Right? The explicit statement is right here. This needs to not take more than 9 milliseconds to execute. That's what this says. And as long as that's true, the program will be deterministic. And if that assumption gets violated, I can put in some code to handle that violation of my assumptions. Okay? So notice that very careful introduction of non-deterministic behavior. It's non-determinism here is being used to handle false conditions, conditions that are violations of the assumptions. Okay, one last topic that I wanted to just mention and not go into in a lot of detail. Initially, when I started working on Lingua Franca, I was pretty sure that determinism would come at an intrinsic cost in performance. It turns out that's not actually the case. So this fellow, Christian Menard, who's a PhD student at Dresden, did a very extensive study over the last few months of the performance of Lingua Franca compared to state-of-the-art actor models. He was comparing against two primarily, ACA, which is a non-deterministic actor model that's pretty widely used in cloud computing cases. This is implemented in Scala and Java, so it's in the Java ecosystem. And we were nervous about doing comparisons against Java because we don't have a Java target yet in Lingua Franca. And we didn't want things to look strange just because we're comparing Java to other languages. There's another actor tool that's pretty popular. It's written in C++ called CAF. And it turns out that ACA is very competitive with CAF anyway. But Christian took a benchmark suite that had been used previously in the actor community. It doesn't take any advantage of the determinism of Lingua Franca. So these programs are all non-deterministic programs, okay? But we can implement them. And we found that for almost all of them, we either match or exceed the performance of these systems. There's some anomalous cases. So this one called Big, right up here, for reasons that we don't understand, ACA outperforms CAF by a lot and outperforms us by even more. And so one of the things we're doing is trying to figure out why. What's strange about that particular benchmark? Because all of the other benchmarks are exhibiting quite a different story. The other thing that's interesting about these benchmarks is that they kind of show how things scale. The horizontal axis here is the number of worker threads that are used. And these benchmarks were run on a machine that had 24 cores. So it goes from 0 to 24 worker threads. And you can see that for some of these applications, so the light blue here is ACA, which is the Java-based framework. And you can see that as you add cores, this particular benchmark runs faster. For our, this one, I guess, was not implemented in CAF. But for our C++ target, it also trails off, but it significantly outperforms by a factor of 4 ACA. The C runtime was run not in parallel here, so that was just it didn't depend on the number of cores, but it also outperformed ACA. But then there's some others where, as you add more cores, here this one's pretty dramatic. As you add more cores to this benchmark, ACA slows down rather dramatically. The more workers are put into play, the slower it gets. Whereas our implementation stays pretty steady. But then there's others where that concurrent dictionary, again, the purple is our C++ target. You can see that the execution time increases with the number of cores for that one. It's not an uncommon situation. You know, many people just sort of naively assume if you add more cores to a problem, your program's going to run faster. Often it doesn't. Okay, it can even run slower, sometimes rather dramatically slower, because there's a big cost to the coordination across cores. Here's two rather nice examples, I think, where we really do well. This is this ping pong example, very simple example where you just have a large replicated pairs of components that are just sending messages to each other. There's no parallelism in the application. And our implementation stays pretty steady, whereas ACA degrades. The blue is Lingua Franca. It's Lingua Franca C++ target. And here's one where CAF does rather badly as you add cores. ACA does really quite well, better than we do. But ACA stops scaling about 8 threads, whereas we continue to decrease. So there's a lot of nuances in this, in interpreting this data, but the high order bit is that the assumption that I had made, which is that to get a deterministic framework, we would pay a price in performance. That's not true. And we've demonstrated that that's not true, that you can get determinism without sacrificing performance. So some of the active research that's going on in this parallel execution framework is more aggressive parallel execution. So don't just base it simply on levels. We've had some missteps with that. So in particular, we were about to submit a paper with an extremely clever technique for parallelizing these lingua franca programs. And the paper was almost ready to go. And one of us realized there was a serious flaw, came up with a counterexample that showed that this strategy actually didn't work. And it introduced a non-determinism in the execution. And we had to abort that. And we haven't figured out how to salvage this very clever method. So it's hard to do. I'll talk a bit about that next Monday. Why concurrency is so difficult. Okay, it's it really is very tricky. One of the key bottlenecks that we have is that we have this shared reaction queue. All the workers are trying to pull jobs from the reaction queue. If each of these jobs has a lot to do, it's not a big deal. But if the jobs are small and simple, then there's a lot of contention for access to that shared data structure. And that can degrade performance. Supporting parallel execution across multiple tags and having more direct support for logical execution time in the language are two things that we're currently working on. And there's also more modern techniques that are built into some hardware to support lock-free mechanisms for handling concurrency. And we're exploring how to take advantage of those as well as part of the research. Okay, so I think I'll stop there. On Monday, I'm going to talk about a whole suite of techniques for doing parallel execution, some of which preserve determinacy, some of which don't. And try to give you a sense of what the playing field is for that whole field of work.